Hello, welcome to this recorded version of The Naked Scientist, which comes to you this week from the Cambridge Science Centre. And we're going to be looking at the question of the energy supplies of the future, because we're starting a series across October where we're looking at the future of things. And so we thought that energy would be a really good place to start. I'm going to ask the panel of scientists that we've arranged for you to talk to this evening to introduce themselves. So let's meet the crew. First of all, who are you?
I'm Richard McMahon from the Engineering Department of Cambridge University. I work on wind power, wave power, things to do with smart grids and what we have to do if we're going to accommodate all these new forms of renewable generation.
I'm Michael Price from the Optoelectronics Group of the University of Cambridge. I work on the physics of new types of solar panel materials, also associated devices like light-emitting diodes or lasers.
Wow, that's quite a collection. Solar panels right through to lasers.
The physics behind solar panels is also really important for these other types of devices.
My name is Erwin Reisner. I work in the chemistry department as a lecturer here at the University of Cambridge, and we work on solar energy conversion, in particular the development of ways to make renewable fuels.
Hi, I'm Shahini Karnarayan, and I work in the Department of Materials Science, also at the University of Cambridge. I work on materials for harvesting little amounts of energy from our environment to power devices which don't require a lot of energy, so small power applications.
What sorts of things?
So I'm looking at things like wireless sensors, portable electronics, wearables, things really that need power on the go that batteries can't provide.
So that's who we have lined up for you this week. Please welcome our four panellists. And of course, a very much regular feature is also the experimental section. Ginny and Dave.
Hi there. So we've got lots of exciting experiments for you tonight. Dave, do you want to tell us what we'll be doing?
We'll be having a look at how most electricity is generated at the moment. We're going to be having a look to see whether we can split water up into its constituent parts, and we're going to see if we can make some electricity by heating something.
Please welcome Dave and Ginny. Well, first up, let's get to talking about your work, Richard. Richard McMahon.
Now wind power is relatively mature. It's making a big contribution to the generation of electricity in many countries. The thing is to reduce cost, improve reliability. I work on generator technology that will achieve that.
When we say wind power, how are we trying to harness wind power? Is that just with windmills, or are there other ways of doing this?
The way that's emerged, if you like, as the sort of standard way of doing it now, after a lot of years of development, is the thing that I think most of us are familiar with, which is the horizontal axis three-bladed wind turbine, which you see everywhere. People have tried other different forms of wind turbine, but the main one for the foreseeable future is the one I've described, the three-bladed horizontal axis machine.
How does that actually work?
Well, you need some wind to start with, and the wind blows on the blades. The force of the wind turns the blades, and if you look at these wind turbines, you see the bit behind the blades, which is called a nacelle. In there, you think it might all be electrical generator. Actually, the generator is about a third of it. The biggest thing is the front bearing, because you've got all those weight of the blades on the front of the turbine, and there's probably going to be a gearbox as well to increase the speed from the very slow rotation of the blades to high speed for the generator.
How much electricity do we produce with wind in Britain at the moment?
Somewhere around 6 to 7%. Obviously it fluctuates. Some years are windier than others. And the aim is to, by 2020, to get to 1 in 7 kilowatt hours produced from wind.
That's quite a lot, isn't it?
I'd agree with you, yes. It shows that wind is really making a significant contribution. And, of course, it's genuine green energy.
Indeed, but the wind doesn't always blow.
That is quite true. We've got a couple of problems to look at. At the moment, we can balance wind with other forms of generation, so there's no worry about the lights going off. In some countries like Germany and Spain, where the wind penetration is getting high, we're having to look at sort of load balancing things, and that's where this whole smart grid comes in. Can we manage the load so as to match the generation?
So this is where the wind stops blowing, so we need something else that can step in and fill the gap while the wind isn't blowing.
Well, depending on the time of day, my friends in the solar business, I'm sure, could help. And, of course, my other topic is wave power, which, as another colleague points out, you can buy the tide tables for about 20 years ahead.
Indeed. Who's got some questions about the future of wind power? Who should we start with? Hands up. One over here. Let me just get to you.
I'm Nelson. How much wind power is produced a year?
to give it in its sort of formal units of, they're actually called terawatt hours, is a little bit difficult. But if I go back to a sort of percentage, it's about 7% of our national consumption. We burn about an average of 40 gigawatts, which is 40,000 million units of electricity. If somebody's good at sums, you can multiply 7% of 40 gigawatts by 365 times 24. I can't do that in my head, I do apologize.
No, neither can I. So if we already are doing this, what can a researcher like you add? Is it just more turbines, or are we trying to make these windmills better in some way?
Well, the analogy I use is that suppose we were in the 1930s and we bought a car, we'd think it was a pretty hot car. You know, we could get to 100 miles an hour, it'd be really exciting, but look how much car technology has advanced. And I think, although it's sometimes hard to envisage, in 30 years, today's wind turbines will seem rather basic, and the ones of the future will be cheaper, more reliable, less noisy, and all the good things that we want.
Shall we find out actually how we generate electricity with a turbine? Ginny?
The way that wind turbines work is they have to convert that motion that the wind's turning the blades round. You've got a lovely little model of it there, haven't you? So the wind's going to hit those blades and turn it round. But then we've just got movement, and that's not what we want. We want electricity. So how are we going to turn that movement into electricity, Dave?
First of all, we need someone to produce some movement. So for this, I need a volunteer. Oh, I think you can come up.
What's your name?
Ines,
And how old are you?
10.
So, Ines, if you can just stand to the side of this. So what I've got here is 2 coils of wire and 2 magnets. And the coils of wire are just wired up to this meter, which measures how much electricity is being produced. And at the moment, how much electricity is being produced?
0.
All we've done is wired the wire into a meter and nothing's happening. Now what I'd like you to do is to take this magnet and poke it into the middle of the coil. If you move it forwards and backwards, can you start to see that needle moving a little bit?
Yeah,
Try a bigger magnet.
it's moving a lot.
So the needle's moving backwards and forwards every time you move that magnet in and out of that coil, isn't it?
Yeah,
So what's going on there, Dave?
So if you move a magnet near a coil of wire, what you're actually doing is pushing little tiny subatomic particles, which are parts of the atoms, pushing them round those coils. They're called electrons, pushing these electrons round the coil, and that's what we call electricity. And the faster you move the magnet and the bigger the magnet, the harder they're pushed, the higher the voltage, and so we get a bigger reading here.
So why did it work better with the second magnet than the first? Because the first one was a bit rubbish, wasn't it?
So, yeah, the bigger the magnetic field, the more magnetic field you're changing inside that coil, the bigger the voltage and the more electricity you produce.
So the second magnet was bigger, so we got a bigger difference. Brilliant. So that's very interesting. If you wiggle a magnet near a coil, you can make some electricity. That's not really what's going on inside a wind turbine, is it?
Pretty much that is what's going on inside a wind turbine. You're moving magnets past coils of wire. Sometimes the magnets are created by putting electricity through the coils of wire, which sounds a bit circular, but it works. Engineers are very good at this sort of thing. And if you move a magnet near a coil of wire, you produce electricity. So here I've got a whole series of coils with a magnet in the middle. If I turn it upside down so the magnet can roll through it.
Oh, there are little lights on each of the coils, and I can see them flash as the magnet falls through that particular coil. So again, this is just a slightly more high-tech version. Rather than having someone there to move the magnet in and out of each coil, you can turn it and make the magnet fall through the coil.
That's right. And basically, everything apart from solar power is based on this principle. You move magnets near coils of wire and it produces electricity.
But that still doesn't seem very efficient. You're having to stop every time and turn it back over. There must be a better way of doing it inside wind power generators and that sort of thing.
So normally, if you arrange your magnets in a circle and your coils in a circle, you can keep on going round and round and round. You don't have to keep starting and stopping. And you can also use gears to speed it up. Remember, the faster the magnet moves, the more power you generate. So you can make everything go in circles and it's much more efficient and you can use a lot of power with quite a small device.
And that must be quite easy for wind turbines because they start off by going round in circles. Is that right?
That's right, Ginny.
But you also look at wave generation, and waves don't go round in circles, do they? They go up and down. Do you have to do something more like what we have here, where you actually have something turning over, and does that make it more difficult?
You're spot on, Ginny. Sometimes we can use, if you like, underwater wind turbines where we've got a tidal current, a stream of water from the tides. But if we want to get power from the actual waves, the bobbing motion, that's difficult. And people have come up with a lot of really clever things going right back to Salter's duck in the 70s to today. And we've got a lot of things on test, but we haven't, I think, got the right answer yet.
What's Salter's duck?
Essentially, it's a duck. It's a thing that sits on the water that bobs up and down with the waves and uses that to convert it to oscillatory motion, moving motion, and then you can do something like quite complicated, and this is the problem. You can pump, say, some hydraulic oil, and then you can use that to turn a hydraulic motor, which is going round, and then you can use one of your rotary generators. Sounds complicated. It is a bit complicated.
So it doesn't work then? Is that a long answer to say it don't work?
Oh, no, it's not that it doesn't work. It's just, as we know, we don't want to pay too much for our electricity. So we'd like to get the system simpler. So A, they run longer without trouble, and B, it doesn't cost so much money to generate the electric power.
Any questions on air or wind or waves? Let's just head this way.
My name's Jess from St Ives. My question is, have we crossed the threshold where we make more energy than it takes to make the wind turbine?
Very definitely. If you think about the embedded energy in a wind turbine, sure, there's steel and copper and concrete in the foundations, but on a good site, you'd expect to pay the energy back in under a year. There's a slightly more subtle question in that as wind turbines get cheaper, you might put them in less windy sites where it takes longer to pay back, so maybe that's a worry, but I'm quite comfortable that we can pay the energy back quickly.
Hi, this is Lowen from Cambridge. Do you think that in the future we'll have bigger wind turbines to capture more energy or smaller, more efficient ones?
I think both things will happen. On land, there doesn't seem to be a really big push to increase the size. The plan there is generally a standard unit, Henry Ford kind of policy, make it cheap, put them up. Offshore, it's a different story because it's a lot of effort to put foundations in. So if you're going to put a foundation in, you probably want to put the biggest wind turbine you reasonably can. So we'll see, I think, growth in offshore size, but on land, I think it'll go for the mass production option.
I'm Edward from a town called Swavesey. What's the biggest windmill you've ever made?
Me personally, I've never had the privilege of building a whole windmill because a lot of things go into a windmill. But the biggest generator I've built as a prototype is 250 kilowatts, which is about enough for 200 houses. But the real size ones are now in the megawatts. And actually, we're building a prototype at the moment. So maybe in a year's time, if we're on the show again, I can show you.
Hello, my name is Frank. I'm from the United States. I was just wondering, is there any kind of technology, you say you're doing wave technology as well, but putting these wind turbines on some kind of buoy system, if they're going to be offshore, to harness the wave energy and the wind energy at the same time?
Now there's an interesting idea, a hybrid, so you can bob up and down and collect the wind. What do you think?
It's an interesting point. We like so far to put our wind turbines on nice solid foundations, both on land and on sea. And people are thinking, well, actually it'd be quite nice to have some kind of floating system. The only trouble is that it's quite a bit of work to make sure it all is reliable and doesn't tip over and so on.
I'm Alicia. I'm from the USA. You always hear about bats and migrating birds and things flying into the wind turbines and getting killed. Is that still a big problem? And if so, is there anything being done to mitigate that?
Well, have to be honest. Wind turbines do kill birds. They kill bats. You said, is it a big problem? And that's quite a difficult question. I mean, in terms of things that happens to birds, they're not very likely to get hit by a wind turbine. There are much worse fates for birds. So, I'm not pleased that we kill any, but you've got to keep it in perspective. And I think we're quite good.
Stephen Halliday from Cambridge. Is there any way of storing electricity which is generated by wind turbines and not used when it's generated? For example, a windy night, lots of energy from wind turbines, no one wants it. Can we store it and use it later?
Absolutely. The difficulties with that is we can store it as so-called pumped hydro. You can pump it up to a high reservoir and let it come out. There are other means. You can use batteries. The only trouble is that we would need an enormous number of batteries. At the moment, the economics do not favor a lot of storage. So we just say run a gas plant a bit harder or not so hard. Or you have Norway as a neighbor.
This is Holly, and I'm from Florida. You said you were building a prototype. Just exactly what is a prototype?
Well, when you design something new, you've got to find out whether it works. and we've designed a new type of generator. We need to build it, test it to see whether, first of all, does it generate power, and does it comply with all the sort of rules and regulations that you need for a wind turbine generator. And we tested it in Norwich, and we managed not to blow up the Norwich electrical supply, so we're very happy.
I'm not sure if that's a slight on Norwich or a slight on your engineering.
I'm George from Ely. I'm just wondering, how do wind turbines catch the wind?
Yeah, good question. So
good
how does the
question.
blade there that you've got on your nice model, how does that actually convert the motion of the air into electricity generating motion?
Well, I can't blow strong enough, George, but the wind coming in has a certain amount of momentum, and the blade shape is such that the wind is deflected off the blades, and that produces the turning force. You know how, like an aeroplane flies, the wing cuts through the air and produces some lift? It's the same principle.
So what you're saying is that the air hits the blade, and because the blade pushes the air in a certain direction, the air pushes back on the blade, and so you actually make the blade move in a certain direction.
That's right, yes.
Any other questions, or are we going to let this man off the hook? We have one more over here.
Hi, my name is Joe from Caldercourt. My question is, I heard about wind turbine it will cost a lot of money to maintain. I just wonder, is it efficient, effective enough for the money we generate from the wind turbine to support the maintenance?
Well, if I were an investor in a wind farm, I would be very concerned about those issues. The general view now is that wind power on land is the cheapest form of generation, including the maintenance costs. That's particularly so in very good sites in the American Midwest.
If there are no more questions, please put your hands together and say a very big thank you to Richard McMahon. You're listening to The Naked Scientists. This edition is recorded at the Cambridge Science Centre. We're talking about the future of energy this week. And we are joined by a wonderful audience. And as well as Dave and Ginny doing experiments, a panel of esteemed guests. Our next expert actually is Michael Price. Now, you're a physicist, is that right?
Yes.
Okay, and what are you looking at the physics of?
I'm looking mostly at the physics of new types of materials for solar panels. We call them solar cells, and a solar panel is just made up of lots of solar cells.
Now, when you look on the roof and you see these solar panels, what are they actually doing? How do they work?
Yeah, so to convert the energy of the sun, which is obviously our most abundant resource of energy, there are a number of steps that you need to undergo. So we think the first step that you need to achieve in a good solar cell is you need to absorb the light. So if you can think of light as particles, we call them photons, you need to absorb that particle of light in your solar material. Then the second step, in the process of absorption, you create an excited electron. So your photon comes into your material, hits that material, and it's going to excite an electron. Got a bunch of these electrons sitting kind of dormant in your material, in your semiconductor. And once you've excited one of these, the electron needs to travel through the material and then out into a conductor, like you're just a normal copper wire. And that flow of electrons is what we call electricity. There are a bunch of problems that could happen. The electrons can crash into each other, they can crash into other atoms, and you lose energy as heat.
So the light coming in from space is hitting the material and it's dislodging some electrons or putting them into a state where they can actually flow around a circuit. How does that get into the grid? Because obviously people want to use their cells on their roof to reduce their energy bill, don't they? And they do that by selling the electricity back to the grid. So how does that happen?
As we all know, grid power works on an AC alternating current. And so you need to convert your direct current, because the sun is a constant source. It doesn't flick on and off at a frequency of 50 hertz. So you need to have just an electronical device to convert your direct current from the sun into an alternating current. And then you've got power for your microwave.
Sounds like a done deal. I mean, how good are these panels? The ones you see on people's roofs, how much energy are they converting into electricity they can use and sell?
So 90% roughly of the solar panels that you'll see on people's roofs are made from silicon. These are pretty good. People have been working on them for 20 years and they're getting up towards sort of 20%.
So when you say they're getting up towards
most of them-
20%, you mean of the energy that hits them, about 20% turns into useful electricity.
Yeah, that's
What happens to
right.
the other 80% then?
A lot of what I study, the goal of improving the efficiency of solar materials is to get that number up. But there's a fundamental limit. The most efficient single layer of solar panel you can get based on thermodynamics. That's just looking at the principles of energy conservation. The energy you put in has to equal the energy you get out, and 30% is the number that we talk about. That's the upper limit. Of course, you can make solar cells more efficient by putting them on top of each other or concentrating the light that goes in on them.
So tell us about this that you've got in front of you. You've got a little demo there.
This solar panel is made of plastic, essentially. That's the active material. If I hold it really close to the light up here, it's going to make a really annoying buzzing noise, which is perfect for radio. So I'm just holding it up really close to a light on the roof, simulating the sun, and it's attached to this frustrating little buzzer here. And you can see it at the same time I can flex the solar panel. It's really thin, it's really light because it's made of these electrically active polymers, plastics, rather than...
So this is different than what you would find on the top of people's
different.
roofs.
And this is what we study in my lab, different types of materials.
So you're trying to reinvent what's on people's roofs at the moment and make thinner, cheaper, lighter materials.
Yeah, we're not necessarily going to replace what's on people's roofs. We might be able to put a very cheap coating onto silicon and improve their efficiency. In fact, that's happened in the last couple of years. But there are a whole bunch of uses for cheaper, perhaps not quite as efficient, but still cheaper, lighter solar. It's really useful in the developing world, for instance. There's still 1 billion people who are off-grid who don't have mains power. If you can supply them with something that's cheap, that's not going to break if you drop it, then that could be a really good thing.
Who's got some questions about solar panels, how solar cells work?
My name is George from Ely. I'm just wondering how you can get the solar cells into a material.
Basically, what consists of a solar cell, you need 2 electrical contacts. So they're going to be made of metal. The way we do it, we start with a piece of glass, and then we have a transparent kind of metallic conductor, and then we just, because the materials we work with don't require extreme processing, we just squirt them on. We can just squirt these materials on, and then we evaporate on another metallic contact.
What's the recipe for the stuff you can just squirt on?
Well, so there's a whole range of things you can do. I was reading today, there's a guy that's been harvesting salmon sperm for use in LEDs, which are just like solar cells in that, a solar cell will convert photons to electrons, electricity. An LED will convert electricity to photons. But in our lab, we use polymers, plastics. I've been researching this new type of material called perovskite solar cells.
Yeah, that's getting a lot of attention, isn't it? What's special about that?
Basically, they have all of the good things of polymer solar cells. They're cheap, flexible. You can just squirt them on. You don't need to grow them painstakingly like you need to grow a crystal of silicon. And they're also really efficient.
So could you have a paint that you could slap this stuff up the wall and turn your garden fence
People
into
always ask
a solar
about
cell?
painting solar cells, but you need the electrodes as well. So it's not quite as simple as
maybe wallpaper or something similar.
But there's already Oxford Photovoltaics who pioneered a lot of the work on these perovskites. They're working on building integrated photovoltaics. So that means that all of the glass that goes on your skyscrapers could have a thin layer of semi-transparent solar panel on that glass. And so they could generate electricity while you work.
While you're zapping the buildings across the street, which happened with the building in London last summer, wasn't it?
Yeah.
This is Holly. I've seen lots of solar panels everywhere in England, but it's always cloudy. Do they still work?
Yes, they do. The new types of materials that we're working on actually work better in low light than the crystalline silicon ones. But it's obviously true that there are places that are better for solar than England. Yeah, the solar panels will work in low light levels, but just not particularly well.
Hi, I'm Will from Swavesey, and I was wondering, does the colour of the cells change the amount of light it absorbs?
Yeah, that's a really good question. The ideal solar cell is a black one because it absorbs all of the light in the visible spectrum. But you can make solar cells of all different colors. But, a transparent solar cell that lets all the light through that our eyes can see is not going to be as efficient as something that harvests that light. You can make transparent solar cells that absorb the infrared. So those are the really long wavelengths of light that our eyes can't see, but they're not going to be very efficient.
So it's like the sort of Model T Ford of the solar panel world. You can have any color you like as long as it's black.
Exactly.
I'm Dwight. I'm also from Ely. Why do the solar cells wear out, and why do you have to replace them after a while?
That's also a very good question, an area of active research. There are an awful lot of reasons. Most solar cells we try and encapsulate to protect them from the elements. Usually, if the encapsulation fails, then the solar cell is going to wear out. In the case of silicon, these solar cells last for upwards of over 20 years. And the reasons for for that can be varied. It can be due to oxygen degradation or water, or probably before the actual material fails, the electronics associated with it are going to fail as well.
Hi, I'm Anthony from Cambridge. I was wondering, how long does it take a solar panel to generate as much energy as was used to manufacture it?
Again, similar to the wind question, the energy payback time for solar panels obviously varies greatly with where it is. If it's in a very sunny place, then the energy payback times actually can be very small, and the energy payback time is going down all the time. But I think I've heard less than a year it can be. But if you put it in a cloudy place, the energy that you've used to create the thing has been, if you haven't made it very efficiently, then that energy payback time is going to be a bit more.
What is that thing that looks like a giant till roll in front of you?
This is a giant roll of polymer solar panel, and it's rolled up here because it's a really good demonstration of the fact that you could print these solar cells off like newspaper. And that's the goal, and that's what could make them so much cheaper. I've also got, it says it on the front here, you're looking at the world's first color production ready plastic display that is flexible. And this is from Plastic Logic, which is a spin-off company of one of the professors in my group. And basically it's a flexible kind of e-reader. Like if you can imagine your Kindle was in color and you could bend it.
It come in handy because the people in customs did that to my Kindle when I was travelling recently. It didn't take too kindly to it. What's your name?
My name's Malcolm and I'm from Longstanton. So the darker the colour of the solar panel means the more sunlight it absorbs and the more electricity is made.
Yeah, that's it in a nutshell.
Do you want to swap places with him? Michael Price from the Department of Physics. Thank you very much. Please show your appreciation.
The Naked Scientists podcast is powered by ukfast.co.uk.
You're listening to The Naked Scientist. This is a special edition of the show recorded at the Cambridge Science Centre with me, Chris Smith, and with you, our wonderful audience. We're talking about the future of energy this week. We're now going to move on to the question of actually how we can produce hydrogen, because hydrogen is regarded as one of the fuels of the future. Why? Well, let's find out. Please introduce yourself, tell us who you are and what you do.
Yes, as I said, I'm Erwin Reisner. We've just heard about wind technology and photovoltaics technology, and both of which essentially generate renewable electricity. What we try to do is really produce a renewable fuel, such as hydrogen as an example. So I think it can be perceived as an extension of photovoltaic research, where we take a solar panel, instead of producing electricity, we just try to produce hydrogen directly from water as an example. In a nutshell, you have water, you shine light on it, and hydrogen comes out. And hydrogen is a very interesting chemical because it's energy rich, so it's a fuel, and we can store and transport it.
How does this work? How can you actually split the water up like that?
So essentially we heard the first part is heavily inspired by photovoltaic research. So we need a light absorbing material where we essentially harvest the photons, what we've heard about, and then instead of producing electricity, we just transfer energy directly to a catalyst. And the catalyst now is a substance that facilitates a chemical reaction. And this catalyst we're using is a catalyst that evolves hydrogen from water, as an example. So essentially, yes, we have physics, and when we talk about fuels, we need some chemistry. That's my specialty, and that's why we try to make fuels, yeah. And hydrogen is only one example. We can think also about liquid fuels to replace fossil fuels, also in liquid form, and all kinds of possibilities.
So you would have a material which would have access to some water. It could split the water into hydrogen and oxygen. How do you get the energy back? What would you do with the hydrogen?
Oh, the hydrogen needs to be stored. So essentially, at the moment, what you would do is you would just pump the hydrogen out and compress it, and then store it and transport it. Or you'd convert it directly into a liquid form of fuel. That's another possibility. So hydrogen can be converted into all kind of liquids by established industrial processes. That's done on the megaton scale at the moment.
It's not dangerous, though. I mean, Hindenburg didn't go down too well. It did go down. That was the problem. But it wasn't too much of a success story from a chemistry and engineering perspective, was it? So isn't there a bit of a danger associated with hydrogen?
Yes, hydrogen is explosive, that's for sure. But so is actually natural gas, and gasoline is also actually quite dangerous and explosive. So I think we definitely have the technology to handle hydrogen as a gas. And it's not much more dangerous than other forms of fuels we're actually handling at the moment.
Well, before we hear more about the technology, I think we should hear a bit more about hydrogen. Ginny and Dave.
So we're actually going to look at a more conventional way of getting hydrogen out of water. So water's H2O, which means it's made up of hydrogen and oxygen. So if you want to get the hydrogen back out, you have to split those molecules up. So how do we go about doing that?
So what you want to do for that, so first of all, I have a pot of essentially water. There's a bit of a salt in there called magnesium sulfate, which basically means it conducts electricity a bit better and makes everything work a bit better. And what I've also got is a power supply, and this will apply a voltage to these two screwdrivers. And so what I'm going to do is I'm going to make one of the screwdrivers positive and one of the screwdrivers negative. Now, if you think of water, it's H2O. The H's are slightly positive and the O, the oxygen, is slightly negative. So if you put a large voltage across water, the oxygen will be attracted to the positive electrode and the hydrogen will be attracted to the negative electrode. And if you put enough voltage on, that will actually split those water molecules apart and you should get gases coming off.
Okay, so we've got a small beaker full of liquid, and you're now putting a contraption made of 2 screwdrivers taped together into it. This looks a little bit dodgy.
We'll try. So I've now turned it on, and something quite interesting is happening.
Oh yeah, can you see what's happening?
I can see bubbles.
You can see bubbles, exactly. So those should be bubbles of hydrogen and oxygen.
That is the idea, yes. So we'll let those build up nicely for a while. And there's an easy way to see whether it's likely to be hydrogen or oxygen would be to try setting fire to it, because we can basically release the energy we put in by putting electricity through the liquid and splitting the hydrogen and oxygen in from water. And if we set fire to it, the hydrogen will burn with the oxygen to create water again and release lots of energy.
So we've just talked about how explosive and dangerous hydrogen is, and now we're going to set fire to some of it.
Sounds like a good plan to me.
Everyone think that sounds like a good plan? So we've got quite a good layer of froth on top of this little beaker now, and I can see Dave is ready with a box of matches. Do I need to get back?
In a minute, yes. The reason why it's creating a froth is I put a little bit of washing up liquid in there, which catches the bubbles, so they're trapped nicely.
Because otherwise they just escape and go off into the atmosphere and we wouldn't be able to set fire to them, which would be no fun at all.
Okay, so here we go. I'll light a match, and I'll put it down to the froth, at which point...
Did anyone notice that bang sounded a little bit funny?
It sounded like a balloon popping.
It did sound a bit like a balloon popping. It was quite kind of squeaky, wasn't it? And that's characteristic of hydrogen.
It was a very, very, very sharp bang, which is because actually it wasn't just hydrogen you're burning, it was a mixture of hydrogen and oxygen. And if you mix hydrogen and oxygen together, they burn exceedingly fast. And actually, if you get the mixture right, they will burn faster than the speed of sound, and you get what's called a detonation, which is really destructive. If it's not perfectly mixed, then you won't get a detonation. And with air, it doesn't detonate quite so well. But yes, you get a very, very violent bang.
Ginny and Dave, thank you very much. So, Erwin, presumably your experiments don't quite go like that.
No, it's safer. Should I show it?
So, Owen, you've brought an example of how you create hydrogen. It's a little bit different, right?
Yeah, so this is a very simple system. That's why I brought it here. Essentially, what I'd like to show is in a test tube, essentially, how you can generate some hydrogen with our energy-saving light bulbs, which are not very energetic.
We needed quite a lot of power to put through our mixture to separate the water out. You're going to do that using less energy.
I will try, yes. So essentially what we have here, this is really just water with some buffer at pH 7. Okay, so there's nothing unusual about it. We'll just pipe this out quickly. And you can see as normal water, it's just fully transparent. This means if you want to generate hydrogen with this mixture, it's very bad because no light is being absorbed, right? That's why it's transparent.
So we need to absorb the light for the energy to split the water, and transparent things don't absorb light very well.
Precisely. This is why I brought this dye here. You can see the deep red coloration, and essentially I just take a bit of that. That's just an organic light absorber. It gives now some color.
Okay, so now it's got a nice bright red color.
Yeah, exactly. So now essentially this dye will absorb light, but we still don't have this catalyst I mentioned before. So at the moment we absorb the light, but it's not good enough to generate the hydrogen. So we really need this catalyst, this substance that helps and facilitates the evolution of hydrogen.
And a catalyst is just something that is used in a reaction that helps something else be produced but doesn't actually get used up itself.
Precisely, yeah. And this catalyst is what we develop in our laboratory.
So that would mean you could use the same catalyst over and over again, just adding more water.
If we have a very good catalyst, yes, but at the moment they do not exist. Except they're very, very expensive and like platinum. But this is a very cheap material, a very cheap catalyst. And at the moment, they're not sufficiently efficient to run for very long. So at the moment, all I do is shake it.
And it's a nice sort of bright orange colour now. It almost looks like it's glowing.
Yeah, it is, exactly. And what I will do now, I will just put it here in the back, and it will probably take a couple of minutes, but then we will see the formation of hydrogen.
So you're going to pop that under a light that's going to effectively, you'd normally do this with sunlight, but it's evening and we're inside, so we're going to put it by a lamp instead. We're cheating, basically. And then we're going to come back to that.
How will you know the hydrogen's been made?
Oh, so essentially we can also light it up, or we use analytical facilities in a chemistry laboratory. We know precisely what gas is being formed.
Setting fire to it sounds like more fun.
Yes, precisely. Yeah, I agree.
We'll come back to that in a second. So tell us a bit more about how you actually are working on this. The ultimate goal then would be so that we have ways of converting plentiful sunlight into a supply of hydrogen.
Yeah, so that is the idea. At the moment, this is a very new line of research compared to wind technology or solar cells, which means we have no commercial applications at the moment. So these are really being proposed at the moment, but it will still take a considerable amount of time really to bring this to the marketplace.
Is it just visible light, or can it use heat? So if we took a waste industrial process that produces loads and loads of heat, or a data center, because I mean one statistic is that the data centers that run the internet are chucking more heat into the sky than they're actually using to run the data center in aircon, and also they're contributing more CO2 than the airline industry. So can we turn that waste heat into something with this technology, for example?
Heat is certainly very interesting and I think should be used much more in the future, but we focus only on solar technology. So, and if you use solar technology, either you run it like our systems just at room temperature, or you work on solar thermal approaches where essentially you also work with heat, with solar concentrators where you work at 1,000 and more degrees Celsius, also to produce fuels that way.
Who's got some questions for Erwin on how hydrogen works?
Hello, I'm Brian from Cambridge. My question is, we heard earlier on that the solar panels turned about 20% of the solar energy into electricity. When you then generate hydrogen, what percentage of the energy is transferred then?
So at the moment, depending on technology, there are two ways. Either we convert the energy directly, which means sunlight goes directly to fuel. This way, the record efficiencies are about 13%. But these are achieved with very expensive materials and effectively systems that do not last very long. An indirect approach would be to couple a solar cell plus an electrolyzer system, as we've just seen before. With such technology, we can probably reach 15% or 20 or even 30% very easily on an industrial scale.
Hi, my name is James. I'm from the United States. You said that technology is new. However, what commercial applications were you looking for this technology, and also what are the hurdles that you face going towards that?
The main hurdle is essentially, there are several, but the main problem at the moment is the cheap price of hydrogen produced from fossil fuels. So at the moment, all the hydrogen we see, which might be quite interesting, is in fact not renewable hydrogen. We might see all the green hydrogen busing driving around, but this hydrogen is all produced through industrial processes from fossil fuels. And this hydrogen at the moment is about an order of magnitude cheaper to produce than any renewable forms of hydrogen. So at the moment, what is really letting us down is the very low cost of hydrogen derived from fossil fuels.
Oh, hi, it's Joe. My question is, can we use dirty water or seawater to generate hydrogen? Because pure and clean water, we are short of it in this world anyway.
Yes, this is certainly feasible, and people have shown that this is possible. So essentially with seawater, we mainly deal with highly saline water full of sodium chloride. But in principle, there's nothing that holds you back to use seawater to generate hydrogen renewably. In fact, it might even help because there's an electrolyte already in the water.
What does that mean?
Electrolyte is simply a conductor in the aqueous solution. So if you want to electrolyze water, for example, you need a conductor, an electrolyte.
So we had added one to our demonstration here in order to make it carry the charge better. So actually, if you were doing this kind of electrolysis to split it, it would probably be better with seawater. In fact, it works very, very slowly, if at all, with pure water.
The only disadvantage with electrolysing seawater is that instead of producing oxygen at the other end, you'll produce chlorine, which is a chemical weapon. So you've got to be careful with that one.
We decided not to go for that tonight.
Chlorine is also produced by industry at the moment. It's quite a valuable chemical. So we might even be able to use this one and produce renewable chlorine this way.
Owen, how is your catalytic breakdown of water going? How are you getting on?
Okay, so at the moment we have produced the first couple of bubbles of hydrogen, which I'm happy to share with Ginny as an example.
Shall we pass it around?
Yeah,
or
gently. As I said, our light source is very
gently,
weak.
he says gently. Is this because it's explosive?
Can you see?
No.
There's some bubbles appearing at the bottom. What is that in the bottom of the test tube?
This is hydrogen that comes from water.
There's a little white thing.
Or this is a stir bar. This is just to stir the solution.
Oh, okay. So there's something in the bottom to stir it, and you
Yes.
can see on there we formed little bubbles of hydrogen.
Yeah, the bubbles like to accumulate at the stir bar.
Okay, so if Dave takes it round, you should all be able to see It's not very many. I think ours was more impressive. But you did do it with light, and we had to use a very high voltage to get that much.
I mean, are you effectively trying to recreate photosynthesis here? I mean, plants are very good at gathering energy from the sun and turning it into a chemical form of energy that they can use elsewhere in the plant or store as sugars turned into starch. So is that sort of what you're doing?
Precisely. So actually we do look at natural photosynthesis, try to learn from it and try to mimic the processes. And the field is in fact called artificial photosynthesis. So we do try to adopt with chemistry and materials chemistry to adopt and mimic processes in photosynthesis.
Everybody, thank you very much. Owen Reisner. You're listening to The Naked Scientists. This is a version of the show which we've recorded at the Cambridge Science Centre in the company of this wonderful audience, and we're talking about the future of energy this week. If you want to get in touch with the show, you can email chris@thenakedscientist.com or you can tweet @NakedScientist. Don't forget to follow us also on Facebook. You can like us on the Naked Scientist Facebook page. Our next guest is Shahini Khan-Narayan, who is a materials scientist who works on piezoelectricity. This is nothing to do with pizzas, nothing to do with deep pan or anything like this.
No.
Tell us what it actually is.
So you've heard about producing big energy and looking for big energy solutions. I work at the other end of the spectrum, which is looking for small energy solutions. And in particular, I'm looking at harvesting energy from ambient sources in our environment to power devices which don't require a lot of power, really. And you might wonder, small power should be a lot easier, but it isn't, because as the devices are shrinking in size, the batteries which you would normally use, for example, to power them, they aren't quite keeping up. And so to enable this technology to progress, we need to look at alternative energy sources. And this is where piezoelectric materials come in. Piezoelectric materials are a special class of materials which, when you distort their shape, so basically, literally when you squeeze them, they produce an electrical charge, which you can then access via a circuit. And the reverse is also true. You can actually apply an electric field to a piezoelectric material and it will change shape.
Isn't this how your crystal in your clock?
Absolutely, and even the way your microphone works, it basically converts, the vibrations from
lighters?
sound. Yes,
Your
those
barbecue
are
lighter and things.
absolutely, yeah.
So you're squeezing a crystal.
Exactly, to produce a voltage, essentially.
But why does that happen if I squeeze a crystal? Why should squeezing a crystal make some electricity come out?
Right, so certain crystals can be thought of as being made up of charges which are separated within them, and we call these dipoles. So imagine a crystal with a positive and a negative charge separated. And essentially what happens is when you squeeze this, you change the position of the positive and the negative charge. So essentially you can imagine that you're creating more of a charge across the surface. And I think Ginny has a demonstration.
Yeah, so we were thinking about this afternoon, and we were thinking it's quite a difficult thing to imagine. So we came up with a little way that you might be able to imagine it at home. So what we've got here is a pillowcase, and you can imagine that this is like one molecule inside the crystal. So I'm going to ask Dave to hold one end of the pillowcase and Sahini to hold the other end.
So the actual crystal will be made up of millions and billions of these all lined up next to each other and stacked in every possible direction.
So if you stretch the pillowcase out nice and tight, now what we've got here is a ping pong ball with a plus sign on it. So that is a positive charge. So if you imagine our molecule has its positive charge at one side, like so, then if we change the shape of the crystal by moving where your hands are, it falls off. But you can see that
So we've squashed the side we've squashed it, the ping pong ball is rolling towards it. So we've squashed the side towards the audience, and the ping pong ball has moved towards that. If we squash the other side, the ping pong ball moves away.
So you can imagine that being like, if every molecule in the crystal is being squashed in the same direction, then your charge is going to move from one side of it to another.
And so if you imagine each molecule has a little bit of charge has moved from one side to the other, then the next molecule, the same bit moves and the same bit moves. So overall, a charge has moved from one side of the crystal to the other side of the crystal, and that produces quite a large voltage, and you can produce sparks with a gas lighter with it.
If you take the voltage out of the crystal, so those charges flow around a circuit like they do in, say, a barbecue lighter, doesn't that leave the crystal without some charge?
And then if you let the crystal relax, then the charge will want to flow back the other way, and then you get a second spark, because you get a spark when you crush the crystal, and you get another spark with the current going the opposite direction when you uncrush the crystal.
And so you're saying, Shahini, that this is a way that we could harness this
Absolutely.
to extract energy that we would otherwise throw away in the environment?
I mean, that's really the key thing. This is energy that is available to us. It's widely accessible. It's pretty much everywhere. You're probably always going to be situated near a source of vibration, so it seems like a good place to start. And what I need to stress is that the amount of energy that we're trying to harness or to harvest is actually quite small. But this is important because if you think of the applications for this small energy, they're really limitless. So a big thing which you might have heard of is the Internet of Things, which is essentially having everything really connected via sensors. Now,
someone told us the other day that he bought a slow cooker, which is on the internet, and he said that he's discovered he can dial in from work to turn on the slow cooker.
Exactly.
But then he discovered that it's the same login and password for every single one of those slow cookers that everyone owns. So then he said, I can ruin someone's beef stew if I just know where to find it.
Indeed. I mean, to be honest, there are lots of security concerns with the Internet of Things, but then that's a debate to be had.
But the question is, how do you
possibly.
power them, isn't
exactly,
it? So,
exactly. And the point is, you can look at the energy crisis from two angles. I mean, we are running out of fossil fuels and we need to look at renewable energy sources. So one way to do it is to look for new ways to produce energy, but the other way to do it is to try and save energy. So the energy which I'm trying to harvest is not necessarily going to light up this building, but it can light millions of sensors in this building, such that you can save up to 30% on your electricity, which
so
sounds
would
like
this
a good
be
deal.
then, say, air currents sort of wafting past something, or if you did it, say, on a light bulb, you could get air currents near a light bulb because it's hot. You could get those vibrations. or
Sure,
something.
absolutely. So, like I said, these are ubiquitous, really. So you could imagine sticking it on your washing machine. That vibrates while it's on.
So anything that moves,
Yes,
you can get energy out of it.
including yourself. So, I mean, I think this is still a bit far off, but in principle, if you could make these devices on a large scale, and if you could integrate it, for example, into your clothing, which is very possible, as you walk, as you move, you could generate enough electricity to charge your mobile phone.
Wouldn't that make walking really difficult, though?
So, as I said, piezoelectric materials have been known for a long time, and usually research has been focused on bulky ceramic crystals, which, as you said, are quite hard to move around with. My research focuses on nano piezoelectric material. We're looking at really tiny amounts of these materials, which the idea is that they should be able to blend into the environment, into your clothing, and practically be invisible for all practical purposes, so that you're not aware that they actually exist, but they are constantly harvesting energy.
So we actually have an example of one of those super bulky piezoelectric crystals that Dave made yesterday. That's quite impressive, Dave. How did you make one of these?
I basically made them by using cream of tartar. And this is, if you heat it up and dissolve it, that's an acid. And then I reacted this with some sodium carbonate. And I spent about 3 hours carefully adding the two together and mixing it up. And eventually the solution went clear, and I let it cool overnight, and you get these really beautiful, quite large crystals.
So they look a bit like a really huge salt crystal, and you can actually see some beautiful geometric shapes on the side.
So yeah, this is because a crystal is when you've got lots and lots of atoms or molecules lining up in a very organized shape, so repeating again and again and again. And the reason why you see the edges of that is that kind of zoomed out to a huge scale. So if you get billions and millions of them together, you get these sharp shapes because that's the shape of the fundamental crystal underneath.
So what are we going to do? I'm not sure I believe that those are piezoelectric. They just look like crystals to me.
It's taken me a while to persuade myself that they are, but now I'm fairly sure they are. What I've done is, it's a bit delicate, so I've got it sitting here. I've put one in a vise, and then I've put two tinfoil electrodes connected to this crystal, and I've wired it up to an audio amplifier and attached that to a speaker.
So the vice is just to hold it still and to hold the electrodes that it's connected to onto it.
Yeah, and so the idea is that any electrical signals which that's produced will be amplified by the amplifier and then should be turned into sound which you'll be able to hear.
Let's give it a go then, shall we? There we go.
So effectively what I've built is a very, very rubbish microphone. with rather better engineering, you can produce a perfectly good microphone, and actually quite a lot of the cheap microphones are made like this.
But the point is you're squashing the crystal, putting a force onto the crystal, and that is, as you say, moving charges around and making them go onto the electrodes, flow to the amplifier, and those little clicks we were hearing, they're the surges of current coming off the crystal.
That's exactly right, yeah.
But we weren't making very much electricity there, were we? And it's quite a big crystal.
So the trick is to, if you can bend the crystal a bit more, you'll get more voltage out of it. Also, if you use much better materials, which is, I think, what you've been doing over here.
Yours better?
I'd like to think so, yes. So, in fact, a lot of research into piezoelectric materials concerns ceramics. So what Dave just showed you was a ceramic material, and the image that comes to mind when you think of ceramics is, they're brittle, they're stiff, and that's exactly the problem. We're talking about an energy harvester which can sustain repeated vibrations or hittings, as you may want to think about it. And so it's important that this material can sustain that level of impact. Problem with ceramic materials is that they are stiff and hence they're prone to mechanical failure. And so I work with piezoelectric polymers, which are a slightly less well-studied class of materials, but they're very interesting because being polymers, they're flexible, which means that they can take a lot more beating and bashing, as it were. And they have several advantages over ceramics. For example, they are actually relatively cheap and easy to fabricate, which is important if you want to make commercial devices.
How much electricity will they make?
So with these nano generators, we're looking at anywhere between 10 nanowatts to a microwatt. And I know that doesn't sound like a lot, but a lot of wireless sensors these days, their power consumptions are also coming down. So it might just be enough to power these devices. And the other thing that you need to remember is a lot of these devices don't need to be on all the time. So imagine a glucose monitor embedded within your body. You don't need to read your glucose off every second. I mean, you might want to, but it might not be necessary. But you might be able to generate enough energy by just your blood flowing across one of these nanogenerators to emit a signal every 6 hours maybe, and that's all you need really. So
How far away are you? Have you got this actually working?
So I can show you a device which I've brought here, and hopefully it will work. It's if I just hold it up. So that little circle there that you see consists of about 10 billion piezoelectric polymer nanowires.
Okay, so just for the benefit of the people at home, what we've got is something that's about 2 inches long by about an inch wide slide of glass.
Yes.
And what's the circle in the middle of it?
So the circle is the device. So the circle is basically about 2 centimeters in diameter. It's about 60 microns thick, which means it's about as thick as the width of your hair. And as I said, it's packed with these piezoelectric polymer nanowires. And if I can get this to work, it should respond to my touch. And that just shows you that it creates a voltage.
So at the top of the box, we've got lots of little red LEDs. And as soon as you touched it, they all lit up.
That's right.
So they're all powered by you touching the device and pressing on it.
So that's really an indicator that you're generating some voltage. And that is sensitive to how much I touch. So just a light tap would give you that. A big push would give you that. So yes, so they are quite sensitive.
So it's like World's Strongest Man competition where you have to hit the thing with a big hammer, but for microscopic people.
Something like that. So, but to be fair, with that particular device, you would need to tap on it at, not very hard for about 20 minutes to generate enough electricity to power an LED. So that doesn't sound very exciting, sitting around tapping for 20 minutes. But the point is that if you can upscale the production, if you can make more of these and connect them in series, then you can bring that time down to a lot less. And that's really the goal, to be able to make lots of these in a cheap and reproducible and reliable manner.
Any questions from the floor? Have you got a question?
My name is Malcolm and I'm from Long Stanton. Why can't you just put a weight on top of the button and leave it for about 20 minutes to power a LED?
That's a very good question, and I'll take you back to the demonstration that Ginny and Dave just gave. The point is that if you leave a weight on, yes, you will generate some charge, but then that's about it. In order to make a current flow in a circuit, you need to be able to do this repeatedly over a prolonged period of time. So by moving back and forth on that material, you produce what is known as an alternating current, and then you can rectify that and use that to power something. But just leaving something on there would just produce a spike of current, and that's about it. But you want this to work repeatedly.
I'm Jasmine from Cambridge, and what's the smallest touch, as in that you can do, as in how? What device, as in, can you touch really lightly and it works very well?
So these piezoelectric materials, as you've just seen, they're very sensitive to the touch, and and nanopiezoelectric materials are super sensitive to very little forces, and we're actually looking at applications where you can put these into, say, biological samples so that you can actually detect cellular motion. So really very, very tiny forces which you would not even be aware of, these can pick them up. So yes, so the answer is very tiny forces. And if I should put a number to that, we're talking on the scale of piconewtons or less.
So pretty small.
Very small, yes.
Any other questions for Shahini?
Lowen from Cambridge. So with this material, you could have it in potentially nearly any electrical device. How easy would it be to recycle it from one device to the other when the device was finished, like clothes, etc.?
Again, that's a very good question. I think one of the drawbacks of these kind of generators is that it is dependent on the actual source of vibration, and that can be very intermittent in nature. So obviously, if you had one of these in your shoes, for example, you wouldn't be walking around all day at the same pace, for example. So to move that into a different application would probably not be trivial. And so I would say that these nanogenerators need to be designed with specific applications in mind.
I'm Holly from Florida. People use phones every day. Do you think you guys could start putting this stuff into screens on your phone?
In fact, I think there's a similar prototype being developed where you have it at the back of your keyboards, because as you're typing away furiously, you can use that energy usefully. So the beauty really is that you can integrate it into just about anything. So yes, I can see applications where you have them on touch screens, where you can harvest the energy of just swiping or clicking on things. Absolutely.
I guess that phones would have to get a lot more efficient before it becomes very useful, because they're using watts at the moment, not microwatts.
Indeed. Oh, sorry. So yes, so I should say that the energy which you would get out of it is still limited, just because there isn't that much energy to harvest. So this would power, maybe one function on your phone, but not necessarily charge your phone. Having said that, as you correctly pointed out, we're at a very unique stage where the power consumption of modern electronics is reduced to such an extent that it is now slowly becoming feasible to power them from vibrations in our environment. So who knows? Someday maybe.
So if you could have an amazing device that you're going to power with one of your things, what would it be?
Oh gosh, I can think of so many of them at the top of my head, but I'm really interested in biomedical applications, really. So tiny sensors which are implantable and which can just run off just your, say, blood flowing through your veins, and which can give out vital information about your blood pressure, temperature, what have you. And I think it would make an enormous impact on healthcare.
So I've got a question that's come in from social media, and Stephen Pates asks, how can the UK be self-sufficient for 100% of its energy needs? So he wants us to not be importing oil, coal, nothing. So I think that's kind of a question for the whole panel. Do you see that in the future, and how far away is it? Who wants to come in on that first? Richard?
Well, I was saying to somebody today, what is the price of not trusting the French? And if we were not to rely on our imports and exports to France, that would cost us a lot of money in extra kit. So actually, I think 100% energy self-sufficiency is not a good goal. I think we should share with our neighbours.
But do you think it would be possible if we did want to or have to?
Of course, but it's probably not the cheapest solution.
I think that energy saving will become more important as we go into the future, and also as more cities are being built, the concept of having smart environments will reduce basically how much energy goes into pretty much everything that you can think about, starting from resource management to waste pickup, and if everything. So if you have lots of sensors in the environment, they can more effectively communicate with each other and also make energy use more sustainable, and then that will have an impact.
Ladies and gentlemen, please join me in saying a very big thank you to our panellists this week, who are Richard McMahon from Cambridge University, also Michael Price, who is a physicist from Cambridge University, Erwin Reisner, who's a chemist from Cambridge University, and Shahini Kart-Narayan, who's a materials scientist from Cambridge University. Thank you also to Ginny and Dave for some fantastic experiments. Great fun. And of course, thank you very much to Greer Jackson and Amelia Perry, who've done a wonderful job on the sound. Thank you very much, and thank you very much for turning up. I'm Chris Smith, this is The Naked Scientists, and do join us again next week. Goodbye.